Hello everybody, I'm Mehdi Mamar. I'm a PhD student in the third year. In this talk, I will present you a work entitled Global Constraint for Closed Frequent Item Set Mining. So to start, what is item set mining? Item set mining is a well-known and the most popular research field on data mining compared to sequence or graph mining. It aims at find irregularities in a given dataset. The traditional example is a supermarket where we try to find a set of products that are frequently bought together. For example, we have here a set of products that represent items and set of customer that represent transaction. An item set is a subset of items. The cover of an item set is the set of transaction where the item set appear. So for example, if we take the item set composed with bread and salad, the cover is the two first transaction. Now, frequent item set mining. The frequency of an item set is the size of its cover. It means the number of transactions where the item set appear. So given a minimum support threshold, the need of frequent item set mining is to extract all item sets such that their frequency are greater or equal to the minimum support threshold. For example, the frequency of the item set composed with salad is equal to, and with the minimum support threshold equal 3, we have the three following frequent item set. It is important to know that the number of a frequent item set is often large, so it was important to identify a compact representation of the frequent item set, and one of these compact representation are closed item set. An item set is called closed if none of its superset has the same support. We say that an item set Q is a full extension of an item set P if the cover of P is equal to the cover of P union Q. It means that we can extend the item set P with Q without changing its cover. So a closed item set does not perform full extension. Now with the previous example, we had this three follower frequent item set. This three item set has the same frequency equal to 3, and the two first one are included in the third one. So we say that the two first item set are not closed since they can be represented by the third one. Here also we have typically an example of full extension. So here we have a cheese is a full extension of salad and vice versa. The third item set has no full extension, so we cannot add another item to this item set without changing its frequency. Several algorithms was proposed for mining closed item sets, but the drawback is that they are dedicated to a particular class of constraints, so adding new constraints require new implementation. The solution to overcome this limitation is to use the CP framework when we have a declarative modeling and an efficient solving based on filtering. Here I present the most popular, the state of art of CP method for item set mining. It's based on reified constraint, and the model is based on two kinds of Boolean variable, item variable and other auxiliary variable representing transaction. The relationship between the item set and the data set is made with the coverage constraint, and we have to have the frequency and closeness constraint. This model offers an elegant way to express a large number of constraints in item set mining, but the drawback is that the model uses an additional dimension of transaction variable, and the model uses a large number of reified constraints, which constitute limitation, especially for a large data set. So, taking into account all of these observations, our goal was to propose a global constraint that encodes efficiently the closed frequent item set mining problem. So we propose here a global constraint that ensures domain consistency with the polynomial algorithm filtering. The global constraint does not need neither refit constraint nor extra variable, and it enumerates all closed frequent item set in a backtrack-free manner. So here we have our global constraint ensure the both frequency, the both constraint, the frequency constraint, and the closeness constraint. So given a data set and a minimum support threshold, the global constraint holds if the item set is frequent and the item set is closed. For example, if we have the item set composed with cheese and salad, here the global constraint is satisfied since the item set is frequent and the item set is closed. Our model is based on a set of Boolean variables representing items. A partial assignment can be partitioned in three subsets. The first one, sigma plus, represent the variable assigned to 1, so present items. The second one represents variable assigned to 0, so absent items. And the last one, sigma star, represent not assigned variable, so free variable. A partial assignment is said to be consistent if the present items form a frequent item set, and there exists no items assigned to 0, such that this item is a full extension of the partial assignment. It means that we cannot form a closed item set without this item. Our global constraint performs three filtering rule. The first one characterizes the inconsistency of the 0. In this case happen if we have items that are full extension of partial assignment, so items that must necessarily be present in the item set. The second rule characterizes the inconsistency of the value 1. If with the partial assignment some items becomes infrequent. And the third rule reasons on absent items with the aim to find if the absence of some items implies the absence of other items. This case happen if the cover of a free variable is included in the cover of an absent item, so the free variable must also be absent. Our filtering algorithm maintained three filtering rule for each free variable. The first and second rule are maintained in OM since we need to check the cover of each free variable. The third rule is maintained in ON times M since we need to compare the cover of each free variable with the cover of each absent item. So to sum up, we have a filtering algorithm with a cubic complexity in time and quadratic complexity in space. Since our global constraint ensures domain consistency at each node on Boolean variable, so our tree search is a full binary tree. The size of this tree is equal to 2 times number of solutions. So we can say that to extract the all of closed frequent item set, the complexity is linear for the number of closed frequent items. Here in this example I illustrate the propagation of the global constraint and the difference with the use of the refit model. So we have this dataset with 5 transactions and 8 items. So it is important to know that the search tree explored by the global constraint is defined only on items variable, where the refit model are the further dimension of transaction variable. So to start at the root node, we have no pruning since there exist no items that are full extension of the empty set. It means that there exist no items that are present in all transaction, and all items are frequent. So we start by a equal 1, and here we consider only the transaction where a appear, and we can see that using the second rule that 6 items becomes infrequent, so we fetch the value 1 from this item. This filtering on a refit model induce a filtering on 4 other auxiliary variable. So the remaining free variable here d is we branch on 1 d equal 1, and here we have we consider 2 transactions and we have directly a solution. We backtrack, so we restore the cover, and here also we have a solution. We backtrack to the initial to the root node, so here we restore the initial cover. We branch on a equal 0, and here we can see that the cover of d is included in the cover of a. It means that Without a, they cannot appear. We cannot have an item set with d without a. So with the third rule, we filter the value 1 from d. Here we can say that the global constraint ensures domain consistency at this node, which is not the case of the refit model. We continue with b equal 1, and here we consider this following transaction. We can see that the item g is a full extension of the items b, so we can add the item g to b without changing the frequency of b, and other items becomes infrequent. So here we have a solution. We backtrack with b equals 0. We see that the cover of g is included in the cover of b. So once again, with the third rule, we can prune the value 1 from g, since the absence of b implies the absence of g. This filtering is also not achieved by the refit model. We continue with c equal 1, and we consider these two following transactions. Here we see that h is a full extension of c, and other items becomes infrequent. So we have solution. We backtrack and we branch on c equals 0. Also we can see that the items h is included in the cover of the items h is included in c. So the absence of c implies the absence of h. So we filter the value 1 from h. For the next branching for the global constraint is e equal 1, but for the refit model is d equal 1, since this value was not filtered in the 5 node. So for the global constraint, we consider these two transactions. We have f, which is full extension items, and other items are infrequent. We have solution, but for the refit model, we have a failing node, since the value 1 of d is an inconsistent value. So for the next, we can see that all filtering achieved by the third rule of the global constraint are not catched by the refit model, and all of these inconsistent value lead the refit model to a failing nodes. Here we can say that the global constraint ensures domain consistency at each node, and enumerate the frequent closed item set in a backtrack free manner. Now I present some experiment on different datasets with different characteristics. We have compared our approach with the most efficient CP method, CP4EM, and the most efficient ad hoc algorithm, LCM. We have used the solver OR tool, and we have implemented two variants of our global constraint. The first one ensures domain consistency with the tree filtering rule, and the second one ensures a weaker consistency with the rule 1 and the rule 2. So I present some results on three different datasets with different characteristics. So we start to comparing the two variants of the global constraint. Here we can see that the third rule reduced considerably the number of explored nodes. In terms of time, the strong version of the global constraint is always faster than the weak version. Now we compare the global constraint with CP4EM. The first observation is that the global constraint is able to handle all datasets, where CP4EM can achieve an out of memory due to the huge number of refit constraints. In terms of node, the global constraint has always a smaller number of nodes, and this number is sometimes reduced by half. In terms of CPU time, the global constraint is always faster than CP4EM. And since the global constraint enumerates the closed frequent item set in a backtrack free manner, so there is no failing node in the global constraint. In terms of CPU time, LCM remains the leader, but the global constraint is quite competitive as a declarative approach. Here in this second experiment, we have a particular model where the interest is to find k item sets such that the global constraint is satisfied and the item sets are distinct. The size of the item set is bounded by lower and upper bound. We have selected two datasets where CP4EM does not achieve an out of memory. We have fixed the minimum threshold and the minimum support threshold and the upper bound and lower bound. Here we can see that in the both datasets, closed pattern, the global constraint scales well and is linear with k, while the CP4EM follows an exponential behavior. So to conclude, we have proposed a new global constraint for mining closed frequent item set, ensuring domain consistency. The global constraint does not need refit constraint the filtering algorithm is cubic in time and quadratic in space. As a perspective, we plan to extend the global constraint for other classes of item sets, such maximal item set, and we plan to experiment the global constraint with more existing constraint in item set mining. Thank you.